Welcome to the exam video for the motor effect. Let's get started straight away. Figure 1 shows the magnetic field around a copper wire carrying a current. Now remember, whenever you see a wire that looks like this, a straight copper wire with a magnetic field around it, you need to remember that whenever there's a current flowing, so the current is greater than 0, you will have a magnetic field around the wire. The magnetic field will be in concentric circles, and each circle gets further and further apart, showing the magnetic field is weaker as you get further from the wire. The right-hand grip rule confirms, so like this, the right-hand grip rule confirms that the direction of the current is where the thumb is pointing, and the magnetic field will be, in this case, going this way around, so that's anti-clockwise. So the arrows represent the direction of the magnetic field. That's your mark for question 1A. 1B, as the distance from the copper wire increases, the magnetic field strength decreases. 1C, suggest how the field lines in figure 1 show the variation in field strength. Well, the closer the field lines, the stronger the magnetic field. You have to speak comparatively here because you are comparing what happens as the lines get closer together. And that will give you 2 marks. The next question is about a solenoid and measuring the strength of the magnetic field inside the solenoid. So the figure shows the results like this. However, you need to draw a line of best fit. Now remember that we do not want to be too far away from any one of the points, so you must use your ruler to draw a line that goes through most of the points, or if they can't go through every single one, you need to have they need to be very close to the line, or you need to have roughly equal number above and below the points. As you can see, in this case I've got 2 just below and 1 just above the straight line. To determine the increase of the magnetic field when the number of turns on the coil is changed from 12 to 18, we need to firstly mark out where 12 coils would be. Now in this case, each little box represents a half a turn, so I need to count 2 boxes to reach 11, and another 2 to reach 12. And if I read up the y-axis, for 12 I get 0.9 is the strength of my magnetic field, because each little box here represents 0.1, and for 18 I get 1.4, so my answer is 0.5. Now on the mark scheme, they got 1.3 and 0.9, and their answer was 0.4, but that's going to depend on how exactly you draw your line of best fit. Both of these will be acceptable. As long as you've done the method correctly and you got roughly 0.4 or 0.5, you would get the 2 marks. The first mark is for doing the calculation, and the second mark is for getting the answer. The next question is about the strength of the magnetic field being increased. There's 2 things we can do. We can increase the current, because if you increase the current, then you'll have a stronger magnetic field. If you increase the potential difference, that will also cause an increase in the current, which will cause an increase in the magnetic field. The temperature does not affect the strength of the magnetic field, neither does how much you spread the turns of the wire, and nor does the resistance of the wire. If you use a higher resistance wire, that would slow the current down, if anything, so it does not make it stronger. The key thing here is that if you were to make the solenoids closer together, that would result in an increase, but if you spread them further apart, it results in a decrease. For the higher resistance, that would slow the current down, so that means less current flows, and so your magnetic field would get weaker. Magnetic field would be weaker. So that's why it's not those two. 1G. The figure 3 shows the north and south poles of a solenoid. You need to draw the field lines to show the magnetic field around the solenoid. Now, there's a couple of rules. Firstly, the magnetic field always goes from north to south. If you've got north here, south here, your arrows must be pointing downwards. And the other mark is you must have at least one on either side. So if you just drew one like this and one like this, you'd get the mark. However, if you only drew one on one side and another one on this side again, you wouldn't get the second mark. So the first mark is for the arrow, the second mark is for drawing them on both sides, because the field is present all around the solenoid, not just on one side. To make this into an electromagnet, you add an iron core. So remember, an electromagnet is simply a solenoid with an iron core running through it. Question 2. Some people wear magnetic bracelets to relieve pain. Figure 1 shows a magnetic bracelet. There are magnetic poles at both A and B. Part of the magnetic field pattern between A and B is shown. Now, you have to identify what the pole is at A and at B. The way to work this out is, if A is a pole, the magnetic field is going away from the pole. Now we know in all magnets, the field lines always go away from the north and towards the south, so A must be north. The same is also true for B, because the field lines are going away from the pole, and so B is also a north pole. Do not assume that both poles are different. So if you rush this question, you might have put south as one of them, but that would be a mistake. 2B. The figure 2 shows two of the lines of the magnetic field pattern around a current carrying wire. The direction of the current is reversed. Now remember, this should remind you straight away of the right hand grip rule. Right now the current is going down, so the field lines are coming around this way. They would be going clockwise. However, if you were to reverse the direction of the current, your field lines would be going the other way. So the direction of the magnetic field line would reverse. That's the mark. Then is a very simple labeling of Fleming's left-hand rule. We know the thumb is the direction of the force. We know the first finger shows the direction that the current is flowing. The first finger is showing the direction of the magnetic field, because it's F for force, B for the direction of the magnetic field, and I is current, which is the middle finger, and that is showing the direction of conventional current. So on a circuit going from positive to negative, this way round. And that's what you should have drawn or written there, the 3 marks. 2CII, we can see the direction of the magnetic field between a pair of magnets, so we know the direction. We're given the direction of the current in a wire, which is going this way. Now immediately I'm thinking, oh look, they look perpendicular, so there's going to be a really strong motor effect. In which direction does the force of the wire act? Well, we need to use Fleming's left-hand rule. We know that we've got F, B, I. We know the direction of B is this way, the magnetic field. We know the current is flowing that way, upwards. And so my thumb is going down into the page, so that is what we need to write there, into the page. So just 3 changes that would decrease the strength of the force acting on the wire. Well, we can decrease the current in the wire. If we decrease the current, then the size of the magnetic field would decrease around the wire, and so the magnetic force, the force would also decrease. Instead of saying decrease the current, you could also say decrease the voltage or increase the resistance of the wire, because according to Ohm's law, a decrease in current will have the same effect as a decrease in the voltage or an increase in the resistance. You can have a weaker magnetic field, and that would mean the force is weaker as well. And finally, you can rotate the magnet so the field is no longer perpendicular to the wire. So if your wire was still going this way, but your magnets, rather than being perpendicular, you had your magnets like this, and the direction of the magnetic field wasn't at 90 degrees, this is no longer a right angle like it is over here, then it would produce a weaker motor effect. 2D. Figure 5 shows a moving coil ammeter as drawn by a student. Now, we may not have necessarily studied how an ammeter works in detail, but it uses the same effect. It uses the motor effect, as we can see in this case, and we're asked to, first of all, look at the fact that we've got a coil placed in a uniform magnetic field. We've got a current passing through the coil, and the force causes the coil to rotate, and the pointer moves across the scale. So we're told how it works. The question is saying that the equipment has not been set up correctly. What change would make it work? Well, the answer is you need to reverse one of the magnets, because if we look at the diagram, the magnets have the same poles facing each other, but we know that that would mean the magnets would be repelling each other, and the field lines wouldn't be going from one side to the other. So for the motor effect to work, the magnets must be opposite poles facing each other, so you have a direction of your magnetic field lines going from north to south. If you have two south poles, the lines will simply move away from each other, and so there would not be a direction to them of the magnetic field that would allow for the motor effect to take place. You're then asked what the pointer, why there's an issue with the pointer. Even though there's no current, it's still producing a reading of greater than 0. What type of error does this ammeter have? Well, we call this type of error a systematic error, because every time you make a reading, it's going to be wrong by this much every single time. So it's systematic. Another way of saying it is it's a 0 error, because when there is no current, it does not read 0. And a third way of saying that is all the current values will be too big, because they're going to be bigger by this much every single time. Third question is about the motor effect again. Here it's a slightly trickier diagram because our magnets are going into and out of the page. The way we know that is because if we look at the magnets, they're drawn in a way that's 3D, and one of them is in front and the other one is behind. So we need to be thinking, if we were to label this diagram, we would say that the current in this case is going from the positive side of the battery this way, all the way up here, and then this way towards the negative terminal of the battery. So if our current is going in this direction, it's going from left to right. Our magnets are, the direction of the magnetic field is north to south, so it's going from out of the page to into the page. So that leaves two axes that have not been mentioned here yet, and that is up and down. So our answer, which I predict just by looking at this diagram, is going to be about which direction does the force travel. The answer is either going to be up or down. But let's first read the question. Closing the switch creates a force that acts on the wire XY. So when this switch is closed, there'll be a force on the wire. So absolutely this question is about the motor effect. First question is, explain why a force acts on the wire when the switch is closed. There are 3 marks available. The first is for saying closing the switch makes a current flow through the wire. In other words, you are completing the circuit. 2. The flowing current creates a magnetic field around the wire. We know that every wire that has a current flowing through it produces a magnetic field around it. And 3. This field, the one around the wire, interacts with the permanent magnetic field. So when two fields interact, that's why we produce a force, and that's why we have the motor effect, because the field from the magnets is interacting with the magnetic field from the wire to produce a force in a perpendicular direction. That is Fleming's left-hand rule. Draw an arrow on the diagram above to show the direction in which the wire will move. So, like I said, we've already figured this one out. As I explained earlier, the direction will be based on the fact that our magnetic field, our B, is going into the page. Our current, I, is going left to right. So our force, as you can see with my thumb, is going to be upwards. So I've drawn an arrow here to show the force is upwards. It's always a good idea to write it as well as to draw the arrow. The effect this demonstrates is the motor effect. And finally, we're asked, if we replace the battery with a low frequency alternating current, that means the current will switch back and forth in direction. What will the movement of the wire be like? Well, we know if I reverse the current, then the motor effect, the direction of the force will switch. So instead of moving up, when the current flows the other way, it will move down. And because it's alternating current, it's going to keep, the current will keep switching direction, so the force will keep switching direction, and the wire will move up and down, or it will vibrate. So, just to go back to this, if I swapped this for a alternating current, then instead of always going from the left to the right, my current will sometimes go left to right and sometimes go right to left. Every time it switches this way, provided the magnetic field stays the same, the direction of the force will either go up or it will go down. And because alternating current switches from left to right, then my force will go from up to down. So it will vibrate. Finally, the reason is the force continually changes direction, which I've just explained there. If you're still unsure, have a look at this explanation. For if you have an alternating current, the current flows back and forth, so the magnetic field around the wire changes direction continuously. Think about the right-hand grip rule, and so the force, the direction of the force will also change up and down in this case. Add up your marks out of 30 and put the number on the front, and that's the end of the video.